Do you trust in your results when running your FEA simulations? In previous videos, we were working with this forks tractor of a forklift vehicle. During all the process, we saw that the default mesh that the software prepared for this project gave us a wrong conclusion about the maximum stress in the zone under study. We saw that the aspect ratio was really bad, and when we refined the mesh, the results changed significantly. Then we could validate the results of our simulation, which is great. And to achieve that conclusion, I had to do the crucial exercise that we all should do in every project to have the confidence that our results are correct. Today I'm going to show you that exercise. Today we are going to review the convergence analysis that I did for this particular project. Let's get into it. Hi, Carlos here, and for those of you who don't know me yet, I've been more than 12 years validating real engineering FEA projects across different industries. So I created my validation method to train FEA the way industry actually demands. You will find all the details in the description below. Now let's continue reviewing concepts of that methodology. Okay, before we move to our project, I wanted to mention one point. If you already did any FEA simulation training, no matter which software you use, I'm totally sure that you always review it how to do a convergence analysis. The typical exercise is displayed with a hole in the middle where we fix it in one side and pull from the other side. The exercise consists of starting from a very poor quality mesh and moving on, increasing the size of the mesh until achieve the convergence. We do this basically because when we do any FEA simulation analysis, we need to have the confidence to trust in our results. Therefore, the convergence analysis is fundamental. But when you move to a real project, I could observe always doubts in my colleagues. Always questions like, where do we stop refining our mesh? When do we start trusting our results? Where is the balance between accuracy and efficiency? As always, in this channel, we are applying the theory, but thinking how to apply that theory to real projects. Let's move to the forks structure that we were working with in previous videos. Okay, here we are. Apart from the convergence analysis that we are going to perform here, we saw in previous videos that we have more indicators to control the quality of our mesh. In previous video, we were checking the aspect ratio plot and how it's a very useful parameter to guarantee the good performance of our mesh. If we take a quick look, I will compare both plots. Here we have the default mesh versus the refined mesh. And using the corresponding limits of this parameter, we will be able to validate our results. Depending what we are analyzing, as I always say in my training programs, if we are analyzing the global behavior, we will have one limit for the aspect ratio, and if we are checking a very detailed zone, we will change those limits. But as you know, in FEA, we don't just trust in one parameter. We want to be completely sure about our models and check all the possibilities. For example, another parameter which is very useful to double check the quality of our mesh is the Jacobian ratio. Let me quickly show you the Jacobian plots of this model. Here we have them. This is another geometrical parameter that, based also on the shape of the elements, help us to check the quality of our mesh. We will enter into more details of the quality check parameters in next videos. Now let's review how I did the convergence mesh analysis for this particular project and how we achieve a model where I can trust the simulation results. If you like the content of this video, I will really appreciate you a like, and don't forget to subscribe so you don't miss any of the next videos coming. And if you want to learn how to actually apply all of this in real engineering projects using my validation method, you can find all the details in the description below. Let's continue. Okay, to show you the mesh convergence analysis, we are going to use the last model that we obtained in the previous video, where we just refined partially the component. This will allow us to move faster when refining our mesh. Okay, here we have it. You can see where I prepared these cuts here and here, far away from the corner, so we have enough distance to do the mesh transition far away from the zone under study. But avoiding refining the complete component. Let me show you the mesh. Okay, here I define my first mesh control to see how much variation I had in my study zone. The size of the mesh is still large, but here is fundamental to move step by step in order to understand all the process. Let me show you the stress plot. Okay, here we have the maximum value, as always, in this region, and the stress that we obtain is 256.10 megapascals with this mesh size. Let's quickly compare with the default mesh so you will see the evolution. Okay, here we can see how this little refinement that I did improved the transition of the mesh in the zone, and it started to transmit more confidence, right? Okay, let's continue. I will exit from here, and now I will move to the convergence number 3 study. Okay, for this study, I just went to my mesh control, right click, and I modify the mesh size. I already ran it, so let me show you the results. Okay, now we are starting to see very nice mesh here in our zone, and the stress value is still increasing from previous simulation. Good. This is an indicator that we need to continue refining our mesh in order to see if in the next iteration it's still increasing or it's starting to stabilize. Before we move to the next iteration, we can check how the computational cost is increasing. Okay, here we have the summary table. For the moment, the increase of elements and nodes and the degrees of freedom, it's not significant. We need to highlight that as we are using the default mesh in the rest of the structure, this simulation is running in 5 seconds, which is great. Okay, let's move to the next iteration, number 4. I already prepared it, so I will move directly there. Again, I went to my mesh control and decrease again the mesh size of the model of this region to 25 millimeters, and let me show you the results. Okay, the stress value now increased again, and now it's almost equal to the yield of the material. So we overlapped it a little bit, but it's there, just on the limit. I need to say that the values are not increasing so sharply, and this is indicating that we are achieving a good behavior in our detailed zone. However, as we didn't achieve a constant number yet, we need to continue reducing the mesh size until we achieve the convergence. I don't want to bore you, so I will prepare all of them and I will show you the results. See you now. Okay, here I have the last model that I prepared. In the bottom of the screen, you can see all the tabs of the simulations that I used until now. At the beginning, here we have the default mesh, and here I have all the convergence studies that we were using for this convergence analysis. We are looking now at the final model that I ran. We can see how the mesh is super good and stable, right? And to be honest, using the techniques that we reviewed in previous video of meshing controls, I could do it much faster, since for the rest of the structure I'm using the default mesh. Here we can see that the peak we achieved is around 300 megapascals, which is the value that we conclude in previous video where we validated the results, if you remember. If you didn't see that video, I highly recommend you to take a look. I will leave you the link below. Okay, now let's move to my slide where I'm going to show you the final results and the conclusions. Okay, here we are. First of all, I'm showing you the table where I report all the iterations that I did. We can see the von Mises stress values per iteration, and I also added the number of elements, the degrees of freedoms, and the running time. As we reduce the mesh size, we obtain a more accurate model, but we increase the computational cost. Let me show you the graph. The green line is representing the von Mises stress. We can see the evolution of the results until we achieve the convergence at the value of 300 megapascals approximately. I also added the red line to monitor how the degrees of freedom are increasing as we reduce the mesh size. The interesting point here, and this is the main reason why this study is worth it to do at the beginning of every project, is the differences between the iteration number 7 and the number 8. The stress value we obtain is practically the same because we achieve the convergence, but the number of degrees of freedom increase drastically from iteration number 7 to iteration number 8. We are talking about 100 150% of increase. And this is what we are going to say during this development process of this project because of this analysis of convergence. Therefore, we can conclude that we obtain the optimal size of our mesh, which is the corresponding to the iteration number 7. Interesting, right? In the last column of the table, we can see also the runtime. It increased as we reduce the mesh size. But considering that we are using the power of mesh controls from previous videos, we can see how even reducing the mesh size a lot, as we just did it in a region of our model, the time increase is not dramatic. So I wanted to show you the comparison of the runtime between the iteration number 7 and the complete model that we remeshed in previous video. If we check the model where we use the refined mesh in all the structure, we were using more than 333% of degrees of freedom in that model. So the runtime will be much longer, but we will avoid that after applying these techniques. All of these techniques that I'm showing you are very powerful because in larger models is where you can make the real difference. Optimize always your FEA simulation to the maximum level to increase your efficiency. Let me know in the comments what do you think about all of this. And I have the last question for you. Until now, we have been working with static analysis and linear simulation. Therefore, do you think that the fact that we crossed the yield of the material is affecting our convergence analysis conclusions? Let me know in the comments what do you think. Of course, we will continue investigating these interesting topics in next videos. And if you want to make the difference and learn how to actually apply all of this in real engineering projects using my validation method, you can find all the details in the description below. Subscribe if you haven't yet. See you in next simulation.